All right, welcome back to another episode of Science with Surback. Subscribers, what you're going to be able to accomplish or be able to do is follow along with section 16.2 notes, which discusses heat in chemical reactions and processes. So before we get going on section 16.2, there's a couple objectives I'd like you to meet by the end of these notes. Number one, describe how a calorimeter is used to measure energy absorbed or released. And then number two, explain the meaning of enthalpy and enthalpy change in chemical reactions and processes. So we're going to get started here with the definition of what this thing called a calorimeter is. And so a calorimeter is an insulated device used for measuring the amount of heat absorbed or released in a chemical reaction or physical process. So I'm going to pause and write that down. All right, so there is the definition written down. Now, a couple of things with a calorimeter. Number one, it's actually a relatively simple device that's able to tell us a lot about the heat exchange that happens in a chemical reaction. So I'm going to pause the video and I'm going to show you what a simple calorimeter looks like. All right, so right here in front of us, I have a simple, what we call a coffee cup calorimeter. Now, this calorimeter has two styrofoam cups, which keeps the contents inside the cups. I don't have anything in here, but it keeps the contents really well insulated. And then I have this cardboard top and a thermometer. So the cardboard top, again, prevents that heat that happens in a chemical reaction or process from escaping out of the top. And then two, the thermometer allows us to measure what was the change in temperature, which ultimately leads to a change in heat, or the heat that we can actually be able to calculate. So again, relatively simple, but it actually tells us a lot about what is happening to the heat or the heat exchange in a chemical process. Pause the video and get back to notes. All right, so a couple of things with a calorimeter. Number one, most of the time, a calorimeter is going to use water. And that's because it's readily available. We know a lot of things, especially on the heat side of water. And then number two, it is going to use the same specific heat formula that we've seen before. And that specific heat formula is Q for heat exchange equals C times M times delta T. Now, the only difference between what we talked about in section 1 and what we have here with a calorimeter is that we have two Q's. The first Q is a positive, which means the heat exchange, and it's a positive heat exchange by the water, and that is set equal to the negative heat exchange. So that means heat was lost by a substance. Now, most of the time, this substance, not always, is a metal. So you heat a metal up, you dump it in some water, the metal gets cooled off, the water gets heated up. And again, that's really the simplistic version of a calorimeter. Now, moving on to thermochemistry. What a calorimeter allows us to do is it allows us to see, or allows us to calculate the heat exchange for a chemical process. So that leads us to thermochemistry. Thermochemistry is simply defined as the study of heat changes that accompany chemical reactions and phase changes. So I'm going to pause the video and write that down. All right, so the notes show the exact detailed definition of thermochemistry. Now, with thermochemistry, we have to be specific about what we are talking about. So there are three different terms associated with thermochemistry. The first of which is the system. So the system is the specific part of the universe that contains the reaction or process we wish to study. So with that in mind here, the system, if we were to get this calorimeter that I have sitting out here, the system would be the contents, the only thing that's in this particular coffee cup calorimeter. Now, the surroundings, on the other hand, the surroundings are defined as everything else other than the system in the universe. All right, so again, it's everything that we're not specifically looking at. So the universe, if we had a substance inside this coffee cup calorimeter, that would be the system. The coffee cup, the inner walls of the coffee cup, and everything else in the entire universe would be considered the surroundings. So the surroundings greatly outnumber the system in any thermochemical system. And then we have the third term here, which is the universe. Now, the universe is defined as the system plus surrounding. So again, simply put, the universe here is the system plus the surrounding. So it's everything that we're looking at here in thermochemistry. All right, so we have another term that we need to talk about, and that term or that concept is enthalpy. Kind of a funny word here, but the enthalpy is just defined as the heat content of a system at constant pressure. All right, so again, key thing here, it's at constant pressure, which think about the pressure in the classroom. It's not going to change a whole lot. So we can look at enthalpy as that heat change or heat content of a particular system. Now, with this business of enthalpy, we have to talk about a couple of different things. And those two things is an endothermic versus an exothermic reaction. So the first thing here is going to be an exothermic reaction. And so for an exothermic reaction, what happens here is that the enthalpy of the products are less than the enthalpy of the reactants. So what happens here is this. Number one, the heat change from start to finish, the heat change gives us a negative value for enthalpy. So what we need to write down is this. In an exothermic reaction, heat is lost by the system to the surroundings. Now, one thing I forgot to talk about up top here, enthalpy. The way we look at enthalpy is this, or the symbol that we use is this. The symbol for enthalpy is just H. Now, when we talk about change in enthalpy, we look at delta H. So I'm going to write that down. Change in enthalpy, that is delta or triangle H, change in enthalpy. So we can get back to an exothermic reaction. We have heat lost by the system to the surroundings. So what happens here is this. We have our enthalpy, H, of our products. In our chemical reaction of our products have a smaller enthalpy than our reactants. As a result, what happens here is that our total overall change of enthalpy in a reaction, and I'm going to abbreviate this as RXN, that stands for enthalpy of a reaction. This gives us a negative value. So it's going to be less than 0, and then in parentheses, I'm just going to put negative. Now, on the flip side, we also have something called an endothermic reaction. And so in an endothermic reaction, we are going to have heat gained by the system from the surrounding. Now, in this case here, our enthalpy of our products is greater than the enthalpy of the reactants. So, in this case here, when we look at a reaction or the change of enthalpy in a reaction, which again I'm going to abbreviate RXN, this time it's going to be greater than 0, or this delta H will be positive. So surprisingly, depending on if delta H is positive or negative, tells us a lot about the thermochemistry of a particular reaction. Now, we can move on. We can actually do some enthalpy reactions or enthalpy calculations without doing a whole lot, or without doing a chemical reaction. And that's when we have this standard enthalpy of reaction. So a standard enthalpy of reaction is this. We have to have a reaction at 25 degrees Celsius. So this is at 25 degrees Celsius, which, if you converted this to Kelvin, is 298 Kelvin. So if we have that occur, we can do some pretty easy standard calculations. So right here it says, calculate the standard enthalpy of reaction between ammonia, NH3, and oxygen, which forms nitrogen dioxide and steam, or H2O. And now it tells us, hey, this reaction occurs at 25 degrees Celsius. Now, looking at the reaction, that doesn't tell you a whole lot. So what we need to do is, once again, use our beautifully periodic table packet, and we need to turn about 3/4 of the way. And what you'll find is this heat of formation values. Now, we're going to use this in just a second, but for this particular problem, the way in which we solve, or the way in which we find the delta H, or the standard enthalpy of reaction, is we have to use a pretty standard format. So the standard format that we use for this is delta H of the reaction, RXN, is equal to the sum. That's what this funky looking E symbol looks like. It is the sum of our N, which is going to stand for moles, our moles times our enthalpy, which is our H. Now we subtract that, and we subtract that. This is for our products. Products minus the sum of our N times our H for our reactants. So this is a weird formula, but it'll make sense here in just a second. So we want to find the delta H for this reaction that's described in this above statement. So the delta H of the reaction is this. We need to, I'm going to start out with brackets. We need to first take the number of moles, which is equivalent to the coefficient in front of whatever substance. So in this case here, we are going to take 4. This is 4 moles times this enthalpy, this standard enthalpy of reaction, 4 NH3. So what we do here, we find NH3, and there's a lot of substances on here. And I know you can't see it very well, but right here where my finger is, we have NH3. Now, what we also have to do is check, does that state of matter match out? So for this chart, NH3 is a gas. We want NH3 as a gas. So yes, it does match out. What we have here is we have negative 46.11, and the unit for this is kilojoules per mole. So we write this down. We say, hey, all right, hey, pause what we're doing here. Made a minor mistake here, and that's this. It's products minus reactants. Here's what happens. We still can use this 4. This 4 moles is for NO2. So, again, 4 moles for NO2. I looked up the wrong value. Always do products minus reactants. So this chart, once again, we find NO2. And on this chart, we have it right here. NO2 is 33.18 kilojoules per mole. So what I do is I write down 33.18 kilojoules per mole, and I close the first set of parentheses. Now, what I do is this. I add, open the parentheses, the number of moles, which is the coefficient for water vapor, so 6 moles, times the value we found in this chart. So this value we find in this chart for H2O, if you look here, we find H2O. Now we got to be careful. There is H2O as a liquid and H2O as a gas. So we want a gas. So we double check our numbers here. This is negative 241.818. So what we do here is we put negative 241.818 kilojoules per mole. Now, this is just the products. We have to take this big number and we have to subtract it from the reactants. So we start out here and we use 4 moles for NH3 because it's a reactant, and we multiply it by that value for NH3, which comes from this chart. And so NH3, we have it as a gas. Its value is negative 46.11. So the value here is negative 46.11 kilojoules per mole. Close the parentheses. We add to the coefficient, which becomes our moles. So there's a 7 out in front of O2, so that means 7 moles of O2 times the value for O2. Now, O2 is a gas, and so if we look on this, the value for O2 is 0. So we have 0 kilojoules per mole. Now what we can do is we can do this calculation. Now, one thing that I have forgotten is this. If something is standard enthalpy, what we would have is this, and you've probably seen it on this chart. This little circle, this little dot, represents that we're at standard conditions. And so all I'm going to do is add this little dot next to delta H. Not a huge deal. It just says, hey, we are at standard enthalpy. All right, so what I need to do is this. This is really important. If you do it all in one calculation, you have to be cognitive of your parentheses. So what I'm going to do, these brackets, I'm going to represent these with double parentheses. So I start out with a double parentheses, 4 times 33.18, close just one parenthesis, add 2, open the parentheses, 6 times negative 241.818, close that parenthesis, and close this to represent the bracket. Now I subtract that from double parentheses, 4 times negative 46.11, close this parenthesis, add 2, 7 times 0. Close that parenthesis, and then I press enter. So this value here, it is in scientific notation. And so what I'm going to do is this. I'm going to perform the same calculation, but I'm going to put it in our other mode, which is, call it normal mode there. And what I'm going to do is I'm going to perform that calculation. So when I did that off screen just to be safe. When I did that, the value for the delta H of the reaction becomes negative 1,133.748 kilojoules for that reaction. So this equals negative 1,013.748 kilojoules. And if we look here, this is the negative delta H. And so what that means is that this is an exothermic reaction. So I know there was a lot of terms thrown at you for this video, but this is a lot of good chemistry happening right here. This is a lot of standard things that you'll do in the Thermo Chem unit. As always, I hope you've enjoyed this video. If you had, like, and always remember to subscribe.